What's up, everybody? I hope that you are doing well. We've got less than 2 weeks to go before final exams start, and so far, reflecting back, I feel like we're generally doing all right in this class. I really appreciate those of you who have reached out to tell me how you're doing. For those of you who haven't been in contact, I hope that you are also doing well, but we're getting close to the end. Okay, so there's some light at the end of the tunnel now, and hopefully you've got all that you need for this class at least in order to succeed on the last case study assignment and the final, which are the only things that are left. So we're getting there. Hang in there. You can do it. All right, we have two main concepts left in the class, and the first is risk analysis, or more generally, how do we think about uncertainty and incorporate that into our economic analysis process. In this video, we'll talk about the concepts and the intuition behind risk analysis, and then in the next videos, we'll talk about the math behind it, how it works, revisit one of the case studies that we talked about on the very first day of class, and then do some example problems. But first, I've got a quick example problem for you so that you can realize that you already know how to do this stuff. So think about this problem where a venture capitalist is considering whether or not to invest in a business opportunity that might be risky. She has a chance to invest $10,000 in this opportunity, and if it succeeds, she'll get $100,000 in return for her support, but if it fails, she would lose the $10,000 and get nothing in return. So what I want to know is what's the break-even value for the probability of success that would cause her to be indifferent between either investing or keeping her money and not investing in this opportunity. Take a moment, think about it, come up with a value in your mind, and then we'll talk through it. I'm guessing that most of you are probably thinking 10%, because if there's a 10% chance of succeeding, then the average return is going to be $10,000, and that equals the investment. If that's what you're thinking, then one, good job, but two, let's also think a little bit more about what that actually implies about how we view risk. The fact that we're saying we're indifferent between investing something with certainty and taking a risk that on average would provide the same amount of benefit says that we are something called risk neutral. That we're indifferent between taking a risk and taking something that's certain as long as they provide the same average outcome. That's actually kind of unusual, and we'll come back to that in a bit at the end of the video when we connect it to utility theory that we had talked about earlier in the semester. First though, let's talk about uncertainty in general. For our class, uncertainty is not any more complicated than the way that you already think about it. We just don't know everything about a system, so we can't predict things exactly or specify what the state of a system is or what the outcome will be. In this class, we've primarily talked about how economics should be guiding the decision-making process. So when we think about uncertainty in our context, what we want to know is what's the best decision that we can make given the state of knowledge that we have about our system, and what additional information that we could potentially gather would cause us to change our decision. Before we can decide what additional information we need to gather in order to either characterize or reduce uncertainty, we need to know two things. First, we need to know what are the kinds of quantities in an economic model that can be uncertain, and then we need to know exactly how they are uncertain. Those are going to guide us in deciding how to incorporate that information into an economic analysis. So the first sort of thing that we think of when we hear the word uncertainty is probably randomness. Things that have some probability distribution from our perspective in that they are unknown but measurable. We might have an estimate for it, we might take an average, or we might even use an average and a standard deviation and some assumption about how it's distributed in order to incorporate it into an analysis and somehow. But the bottom line is that there are some sort of parameter in our model that has an element of chance to it. The next thing is a decision variable, something that decision makers can exercise direct control over. Depending on our particular perspective in our analysis, this may either be something that we would treat as a scenario of saying, okay, well, if I was going to decide this, then here's what the present worth of this project will be. But if I decide that, then my present worth is something else. On the other hand, we might have situations where the decision is actually out of our control. It's up to some decision maker that's not part of our analysis directly. An example of this would be environmental regulations. There's uncertainty about whether or not some particular chemical that a company wants to use in their production process is toxic or has some sort of environmental impact that's negative and potentially could be subject to regulation. The company, when it's deciding whether or not it wants to use this chemical or some other alternative and is doing the analysis of that, they have to consider whether or not that chemical is ultimately going to be banned or taxed or regulated so that they can only use a certain quantity of it. Next, we have value parameters. This represents some preference of the decision maker, and it comes into play when we have a multi-objective context, particularly if we have multiple impacts of a project that are not all monetary. One example that we've already talked about earlier in the semester would be growing corn to produce ethanol. We have the actual cost to produce the ethanol as well as the price that we can sell it at, but we also have greenhouse gas emissions. We have impacts on water consumption if the corn has to be irrigated to grow it. We have water quality impacts if nitrogen and phosphorus fertilizers are used and then leach off into the water supply into a nearby stream. And we also have the potential for land use change if we are clear cutting a forest in order to grow corn on that land. So there are a lot of different impacts, and we don't know exactly in the eyes of the decision makers or in the eyes of stakeholders who would care about the decision that's being made. We don't know how much they care about the greenhouse gas emissions versus water quality impacts. That would be expressed by some sort of a value parameter, which, because we can't look directly into the head of the decision maker, is going to be uncertain. Just like there are lots of types of quantities that can be uncertain, there are also lots of types of uncertainty. In some cases, quantities are uncertain because we don't know them with precision, can't measure them accurately, or we can't predict them accurately if they're in the future. In the case of decision variables, they're uncertain only because the control hasn't been exercised yet. The decision hasn't been made, and so we don't know what it will be. Depending on our perspective, whether it's our decision to make or someone else's, the decision might be viewed as either an empirical parameter or it could be a decision variable for us, in which case we might treat it as a scenario. And then other quantities are uncertain because we can vary in how we represent them in a model. For example, in the case study assignment, there was uncertainty in the first phase associated with the temporal resolution of the model. By using an annual average value instead of an hourly value for things like solar irradiation and energy demand, we are introducing uncertainty into our model because we're not modeling it as accurately as we could be. Those types of quantities are often what we call a domain or an index variable. What's the index by which we are incrementing time in the model? Oftentimes we try and represent a model as simply as we can while maintaining its accuracy, but those are trade-offs, and part of the case study assignment's purpose is to illustrate the difference in the present worth of this solar panel project depending on how you model it, and how much uncertainty you're resolving by going from an annual average to an hourly operations. In terms of what we do about uncertainty, treating it probabilistically is probably the most common thing that comes to mind. We would treat the value of some uncertain quantity as being drawn from a probability distribution, and then we might be able to analyze the outcomes that result probabilistically using uncertainty quantification. For example, if you've had a probability class, you know that if you have two different random variables, that the expected value of their sum is going to equal the sum of their expected values, as long as they're independent of each other. That would be a situation where we're treating uncertainty probabilistically and propagating that uncertainty through our model, starting with the mean value of some of the input parameters and calculating the mean value of the output. In other cases, we might treat uncertainty parametrically, meaning that we're going to repeat our analysis for a range of different possible values for the uncertain quantity. This is like what we did when we were creating a spider plot to conduct a sensitivity analysis. With that example, we were looking at when does it make sense to replace our current Honda Civic with a newer Toyota Yaris. And we were repeating the analysis for a range of different values for the gas price, for the mileage of the car, for the O&M costs, and so on, to look at how much the present worth of our different alternatives varies as a function of the input parameters. And to explore that, instead of treating it analytically and trying to calculate what's the average or expected present value of the Toyota Yaris, we were conducting a parametric analysis, looking at lots of different combinations of values to see how the worth of the project would change. In some instances, we might conduct a parametric analysis because we simply don't know the probability that we should assign to each of the different possible values for an input. In other cases, though, we might do a parametric analysis just to explore the range of possible outcomes that you could get from the range of possible inputs. The switchover analysis is essentially another way of talking about a break-even analysis, where we're going to look at our model to try and discover the values at which point our preferred decision changes. You would also hear this called a threshold analysis sometimes. And then finally, in some cases, we treat things that are uncertain as certain and just ignore the uncertainty in that particular variable. We might do that if we've done some sensitivity analysis of a complicated model and determined that not every parameter really makes a difference in changing the outcome, in which case, to simplify the model, we might just take some things that actually are uncertain and ignore it by giving them a fixed value. In the next video, we'll start introducing some of the math behind uncertainty analysis and introduce a framework for analyzing risk.